Hi, in this video, we want to take a look at transforming target and predictor variables to improve linear models. All right, so previously we took a look at transforming one variable to improve a linear model. So in simple linear regression, we transformed just the predictor or just the target variable. Now we want to talk about transforming both. Now, we've got two game plans for doing this. One is to simultaneously transform the predictor and the target variable. The other one is sequential, where we transform the predictor, then we see what is the best transform for the target, and then we transform the target variable. They usually perform about equally, honestly, but the second way, the sequential way, from my observations, is slightly better, but it does take more time and more work. Right, so first way is that we look and try and find the best way to transform the predictor, and we look to see univariately what's the best way to transform the target, and we transform them both at the same time. The second way is that we transform the predictor variable, then we find the best transformation we can find for the target variable, and then we transform it that way. The second way takes more work, but it slightly gets better results from my observations. And so when we're transforming them at the same time, we're just using univariate data. So we're not considering the combination of predictors and target at all. And so something about transforming sequentially is that we actually end up building like a model. We look at the model, we transform the predictor variable. Now we build an intermediate model that uses the transform predictor variable instead of the regular predictor variable, and then we transform the target variable. So we end up making 3 linear models in this process. All right, so now let's go ahead and look at some code. And for this one, we're just going to use the salary gov dataset that's listed in the textbook. And something I'm going to do to make it easier to interpret things is that I'm going to define the row names in the data set by the job class. So I've got row names correspond to job class, and I go ahead and I just reorder the data. I look through the data. It was in alphabetical order by job class, and for my purpose, I would rather have it in order by my target variable, because that way, if I see something later in the data set or earlier in the data set, I might be able to pick up a trend that's going on. Now, the next thing is to create a color palette. So just like previous, I am taking the Veritas color palette and one different color for each row. And then we go through and we take the order of the target variable, which since it's sorted, it's 1, 2, 3, 4, 5, 6 is the order. It's nothing special. Then we take the inverse permutation function, and then we apply that to the color vector we just created a moment ago. Now, something about this is that if we have duplicate values of the target variable, duplicate values will actually have different colors because by how I'm defining this. But for the visualization, I've not had a problem with this. If I was to invoke like one additional step for using unique salary values, then I could have a more even color scale. But in my experience, it doesn't really make a difference. All right, so let's go ahead and build the initial model. And here we're going to be doing the simultaneous predictor and target variable transformation. So what we're going to do, we're going to take the regular old target variable, regular old score predictor variable, and we're just going to build a regular simple linear regression model. We're going to call it LM for linear model, vanilla. All right, so let's go ahead and take a look at the summary. And definitely got the statistical significance going on. All right. And 0.817 and 0.816, I mean, that's honestly not bad for anything that involves humans. But you know what? We would like to see, can I do better? Can we get something better going on? Because, you know, these residuals are a little bit bigger than I would like them to be. All right, so let's go ahead and plot the scatter plot. Remember, the scatter plot is the most important aspect to linear model diagnostics. And might be a little bit of a curvature going on, something. Maybe it's a little bit spreading out. Yeah, I think maybe we can do a little better. We notice that on the right-hand side, all of these points are above the line. That's not really what we want. We don't want to be able to see like a bunch of points on one side of the line. All right, so let's go ahead and plot do the diagnostic plots for the linear model. Now you'll notice I skipped plot 4. That's because in this scheme, what I'm going to do, I'm going to say background is equal to the color and plot character is 21. Why do I do that? Well, with the wide range of values that we have, if we look at the scatter plots, you'll notice that yellow really isn't going to stand out. It's going to be hard to spot as is, and there's a lot of yellow values. And so what I did, instead of using plot character 19, I used plot character 21, so I can get that dark ring around it to make it pop, make it easier to identify. Well, when I do background, it kind of messes up the colors for plot number 4. So what I'm going to do, I'm going to look at plot number 4 separate. All right, so we can see that we've got residuals, and all these values are above. All these values are above on the extreme ends. That's kind of not, you know, kind of making a smile. And so something that's real nice about the row names, that since I named the row names like I did, you'll see that physician, senior, associate is where this funny point corresponds to. And I can see physician, associate, and library director. So physicians are very different occupations. So it's not really that surprising that the physicians are popping up at library director. That's kind of unusual. Oops, don't want to do that quite yet. Now, the x-axis is along the fitted values, and the fitted values should go pretty well with the observed values. So it's okay for us to see this color trend going from left to right. So every time I look at a plot, I need to ask myself, should I see a trend? Should I not see a trend? Do I see a trend? Do I not see a trend on the color? That will help with my diagnostics. Okay, here we really shouldn't see a trend, but because they're sorted, the lighter values are like the last ones plotted. So here, I'm not too worried about it. I'm concluding that this isn't normal because we have just too many points above and too many points below. And here's a square root of the standardized residuals, or absolute square root of the absolute of the standardized residuals. Fitted value color is okay. Let's look at residuals versus leverage. So remember, leverage will always correspond to the predictor variable. So leverage is going along with their score. And something interesting going on here with that dark aspect. If we have a linear, if there's a linear model underneath, you know, under the hood of the situation, then the leverage which goes along the predictor variable, and the predictor variable, you know, correlates with the target variable, which you see leverage corresponds, you know, to, oh yeah, so it's distance from the center of the predictor variable. So this is okay. This is okay. And we can see that the physician, senior, associate is just way off the scale from everything else in terms of Cook's distance. If this was a full project, I might consider removing that data point just because it's so different from the rest. Now let's look at the fourth plot for regression models. And it's a cook distance one. Now here, it's real nice to see how, like, we can see more of a trend since the way I colored it. Since I colored along the target variable, which is salary, we can see that the big salary ones are the ones that have a lot of cook's distance going on. So that kind of pops out at us. We also see that there's something going on here, but that was not one of the top three, so that was not plotted. Oh, and I misspelled a word. There's an R. Oh, it's not letting me. All right, pretend that that's not misspelled. There's an R there. All right, so right now we're not satisfied with the model. Let's keep digging. Let's see if we can do better. So let's go ahead and plot the density of the target variable. So what we're going to do, we're going to find the density of the target variable. Then we're going to plot it, a line plot, and then we just label it appropriately. Now I'm going to use the rug plot to put little dashes along the axis so I can see where are the actual values. And that helps me visualize. So the rug plot are like these teeth down here, kind of looks like a rug. These are where the actual observations are along the x-axis. And so that gives me a visual impression of where they're at. And the density estimation, we can see that it's skewed right. And that's consistent with that normal plot we looked at earlier. Now let's look at the box plot. All right, so this looks to be skewed right because this tail is longer and we have a bunch of outliers. Now let's go ahead and look at the normal plot. And yeah, this is definitely skew. Definitely. Skew right. When both tails are above, it's skew right. When both are below, it's skew left. For a normal plot. All right, so now we're going to do the same thing, but this time we're going to do it for the predictor variable. So here is their score. All right, a little bit going to the right on the tail, but not a lot more. It's not quite symmetric. It's unimodal at least. Look at the box plots. Yeah, the tail is a little bit longer, on the big side, but not a lot. Normal plot. Now we're seeing some stuff down over here. All right, now what we're going to do, we're going to explore power transforms. Now, there's different functions in R to do power transforms. See which way we go. The first one we're going to look at is the power transform from the car package. So what we're going to do, we're going to take the power transform function and we're going to pass the variable we want, and then we hit summary for it to print out. So the estimated power is -0.1, and it's rounded off to just 0. If we do a confidence interval, it goes from -0.1 to 0.12, sorry, -0.3. So we can see like 0 is in there, which would be the log transform. Remember, 0 for power transforms correspond to the log transform. And here, if we want to do likelihood ratio test that's equal to 0, we can see that the p-value is 0.4. That's large, which means that we go with the null. Remember, equality goes in the null, so equal to 0. So here, this is indicating that so this hypothesis test concludes that the power transform to use is the log transform. And here's likelihood ratio test that no transform is needed. So the null hypothesis is that no transform is needed. The alternative is any, or there is a transform to use to improve the model. And we can see that it's statistically significant. So this is saying that we should be looking for a transformation. Now let's do the same thing on the predictor variable, score. So once again, I take the predictor variable, I put it in the car power transform function, and then I hit summary to print everything out. The estimated power is about 0.6. Rounded off, it's 0.5. And we can see that upper bound, lower bound is about 0.4 to 0.7. Now, let's do a likelihood ratio test that is equal to 0. And we conclude that the power transform is not equal to 0. And likelihood ratio test that a transformation is needed is statistically significant. So we should definitely consider a power transformation. Now we can also do this. So previously we did it with the variables themselves. We can also do this with the linear model. If we do this with the linear model, this is going to say how we should change or how we should transform the target variable only. It's not going to tell us about the predictor. It's just going to say, hey, transform the target variable in this. All right, so when we go through the same thing, so previously in this spot in the power transform function, we had each individual variable for an iteration. Now we're putting in a linear model. And what this is going to do, this is going to work to see, hey, I see that I have a predictor variable. What is the best transformation for y given that I have this predictor variable to work with? And here it estimates the power of 0.13 and gives us a confidence interval of just a little bit bigger than 0 to about 1/4. All right, so now the power transform. So our p-value is 0.05. Oh, right on the boundary, right on the boundary. All right, so here we would fail to reject the null if it's exactly the cutoff, because we're always prone to going with the null. So we would conclude that the proper transform is 0. But it's close. You could use, it'd be reasonable to go either way. And this shows us that once again, we should transform the y variable. Now, there's another way to go about this. We can use the inverse response plot from the ALR3 package. And here we just drop the model in. We tell it how to plot. We tell it what colors to use. Let's take a look. Now, the function is depreciated, but one thing that's nice about this function is I don't have to invoke the entire package. So I like this double colon notation because I just grab the function I need. I don't load the entire package. I prefer to avoid loading packages because it will prevent package confusion, which can be a problem on bigger projects. This is so small, it wouldn't be an issue anyway. Okay, so the inverse response plot concludes that for max salary, the best transformation is 1/4. And that's going to be the black curve. And the black curve, we can see that it's doing a better job tracking than the previous scatter plot. Now, if lambda is -1, we can see that it goes like too low on the right. If it's 1, we can see that it's too high. And then 0 just goes along there. And it spits out some root squared errors. So something to notice about this is that we have 0.25 and we have about 0.9 to the power of 7. And then for 0, we have 9 times 10 to the power of 7. I mean, those are pretty close. And previously, things were saying 0, 0, 0. Now this one's saying 1/4, but it's also saying that 0 isn't far off, honestly. So I might want to just stick with 0, which would be the log transform. Okay, so what we're going to do is we're going to take the information that we've got and we're going to go ahead and do some transformations. So if we look up here, we have about a half for the power transform of score, and we have 0 for the power transform of our target variable. All right, so 0 is the log transform, 0.5 is the square root transform. So let's go ahead and use these. Now, why am I choosing these? Well, honestly, I could do a more precise like decimal transformation, but when I need to go explain it or interpret what's going on, having functions that have algebraic properties like logarithms can make it easier to interpret what's going on. And also, it's easier for people to accept if it's something they've seen before. We've all seen square roots growing up, and logarithms most of us have already dealt with at some point. So we put in the log of max salary and the square root of the score into a linear model. Now you'll notice I'm putting the transformation inside the linear model. That way I just drop untransformed data into the model and it does the rest for me. It's raining right now. I'm going to shut the door. Yeah, the acoustics in this room aren't that great, but there's a bug that just decided to join me. So the acoustics are different now. All right, now if we look at this, is this an improvement? I mean, really, that's really what we want to know. All right, so here, the hypotheses are within machine error of 0, and we can see that we have 0.84 for our R squared both times. How does that compare to the original vanilla model? To go up, let's see, all the way up, all the way up, all the way up. Okay, well, previously we were at just under 0.82, and now we've got an improvement. All right, so we're better than 0.84, where we previously were just under 0.82. So it's a little bit of an improvement. It's not a huge improvement, but it's enough that as long as my audience will accept those transformations, I'm going to run with it. And let's go ahead and do our plots to check it out. So it's a little bit better. And we can go through and we can plot. And so there's still a bunch of points above on both sides. Not really digging that, but it's not that bad. So here, the residuals are looking more normal, especially over here. These are a lot closer to the line. I'm digging that. I'm digging that. I can see that I've got more lateral dispersion, it looks like. It's probably from taking the square root. And I can see that I've got more dispersion among these points instead of having physician just kind of being so far off by its own, like in a whole nother league. It's still up there, but it's not as far from the rest. And now we can see that the most extreme target variable values are not the 3 that are perfectly corresponding to the extreme Cook's distance. So now it's more distributed out. And we want to take a look at the distribution. All right, so here this is the log of the target variable, which remember it was skewed, now it's not. It's a little bit bumpy. It's not really as symmetric as I'd like it to be, but it's better than what I had. Look at the box plot. Looking a lot better. Look at the normal plots. Okay, so tighter to the line, but not as tight as it could be. Now let's look at the transformation of the score. So here we're looking at the square root score. And this looks about as good as you're ever going to get with data, honestly. That's looking pretty good. Looking pretty good. You can see that the box looks symmetric. The box, so each of the two sides of the box look of the same width, vertically, and then the whiskers are the same length. All right, a little bit off, but I'm not too worried about that. From the density plot made me feel okay. It's not critical that it looks like a bell curve, but being symmetric and unimodal is really what I want. All right, so now what we're going to do is we're going to do the transformation sequentially. We're going to transform the x variable first, then we're going to transform the y based off of what we see from the transformation, from the linear model using just the predictor variable that's been transformed. So we've already established that the best transformation, or a reasonable transformation for the predictor variable, is a square root. So what we're going to do, we're going to transform x, and then we're going to build a linear model. We're going to use this model to see what's the best way to transform the target variable. So let's go through. And these residuals are still bigger than I would like, but everything's statistically significant. The p-values are within machine accuracy of 0, so that's good. Ooh, we took a hit on our r squared. So it was about 0.82, now it's at 0.78. Okay, well, that's a little bit of a drop. So we probably won't launch this model, but that's okay. It's just an intermediate to work through. But we've already decided we wouldn't use this one. We would use the one with both transformed simultaneously over this. All right, let's go ahead and look at the scatter plot. And we can see the model. It really hasn't addressed the issues I had earlier. Let's look at the diagnostics. Oh, we see like a line coming down here, and I really don't like that sloping line. That's usually you see something like this when there's like a lower bound that's coming into play on data, and these are kind of like spreading out. So yeah, I would not use the transformed X model. One side is kind of off from being normal. Yeah, we're seeing the same thing on the square root of the absolute value of standardized residuals. Here's our Cook's distance again. And while we're seeing this physician senior associate is way off. So overall, I conclude that I feel like this would actually be inferior to the vanilla regression model. It just wouldn't be worth it to bother with transforming the X value. And let's look at Cook's distance. And yeah, it didn't even address the 3 extremes on Cook's distance at all. So now what we want to do, we're going to take that intermediate model and we're going to use it to find the best way to transform the target variable. So you'll notice what we do, we take the car power transform and we drop in the linear model that has only X transform. And what this is going to do, this is going to try and find the best transformation for Y, given that X has been transformed with the square root transform. All right, so here estimated power is about -0.2. Lower bound is about negative 0.3 to 0.03 negative. Got a small p-value. So we conclude that the best transformation is not equal to 0, and we conclude that we should transform the target variable. So we're looking at around negative 0.2 as our transformation. Let's look at the inverse response plot. And here we can see that, once again, close to negative 0.2 is the optimal one, and I can trace along the X line, and that's not too bad. But look at the blue, it's going a little bit low on the right. Look at the light blue, the teal, a little bit high, and then 0, which is the one that we used in the previous transformation of Y, is going along pretty close to the black, actually. So that tells us if we use like negative 0.2 or 0, we're probably not going to get much difference between the two models. Now, one of them will be the better model, but it's not going to be an extraordinary difference. So here, let's look at the root squared error. So here, negative 0.2, we can see that we have 8 times 10 to the 7. And then, but if I put in 0, it's almost the same value. So that previous transformation with a log probably is a good one to go with. All right, so the author of the textbook went ahead and went with negative 0.25. And I think that's just because it's close to negative 0.2, but it's a more natural number, negative 1/4. That was his choice, and so he picked that. It's a reasonable choice according to the confidence interval. It's not far off from the other values that we've been looking at, so I don't think it's a bad choice. So let's look at the plot. All right. So we have the box plots. And like visually, I can't really see a skewness over this. Oh, maybe this box is a little bit bigger, or this side of the box than this one. So we got QQ norm, QQ line. All right, well, this side got a little bit going off. Here, a little bit is going off. But I'm honestly not sweating that aspect. All right, so now what we're going to do, we're going to say linear model transform X then Y is the linear model with max salary is negative 1/4 transform, and then score is transformed with the square root transform. And let's see what happens. And so remember, the residuals are going to be on the negative 0.25 scale. So this is not the correct scale to be working with. So this is not directly comparable to the other models. But good small p-values, that's looking good. What about our R squared? Our R squared is 0.845, slight improvement. So this would be a reasonable model to go with. I think either model with transformed Y would be a good one to choose. You have to ask yourself, what is your audience more likely to accept, a negative 0.25 exponent or a log transform? Which one is less uncomfortable to them? And when we look at the plots here, so remember, because of the negative in the exponent, things are getting switched around. And honestly, I like this plot the most. I think when I look at this, I personally think that the sequential transformation model is the best one to go with. Looking at our plots. All right, so you can see that we have a lot more even dispersion above and below that middle line for our residuals. We can see that the extremes are above and below. That's making me feel good. We want our extremes to kind of be evening out. Once again, the extremes are evening out left and right. Yeah, I'm feeling a lot better about this. The more I look at it, the more I'm convinced that the sequential ones to go with. Here, I'm not seeing a pattern. There's a little bit of a line going through, a little bit low, but that's not big enough for me to sweat it. Yeah, here we go. And we can see that the extreme values have all like moved up on the Cook's distance plots, instead of having like, you know, that position like way up by itself. Got one more Cook's distance to look at. Oh, and we can see that instead of having them all tight on one side, they're kind of dispersed. That's reassuring because we don't want a pattern in our issues, in our difficulties. All right, so let's look at the summary of the models. So everything was statistically significant. The first model was 0.82 for R squared, both ways. Then we get 0.84, okay. Took a dip, so we're just going to ignore this model altogether. It was intermediate anyway. And then here we get 0.845. So it's just a little bit of an improvement. It's not a huge improvement, but if it's the best I've got, I would go with it. And the diagnostics made me feel more comfortable with the sequential model, so I would go with the sequential transform model. And now here, all of this code is going through and plotting each of the models so that we can compare them. So we do a scatter plot, then we plot the line of the vanilla regression. Now here, I'm going to go through, I'm going to predict all of the values given for each score. And then we're going to take, you know, the prediction for the vanilla model. And then we're going to do the prediction for the simultaneous transformation. Then we're going to do the prediction for the transform X only model. And we're going to do the prediction for the sequentially transformed model. Now, notice every time that I have a model that transforms Y, I have to do the inverse of the transformation. So if it's negative 0.25, I have to take it to the power of negative 4. And up here, where was it? When I have the log transform, I have to undo it with the exponential function. And then the lines function just plots the lines. And I put in a legend so I can see what's going on. So red is the vanilla model. So first and foremost, I can see that the green is the worst model. So that's the transform X only. We knew it was bad. No shock there. Then we can see that the red is like too low, honestly. So I wouldn't want to go with that. And the black and the blue are actually pretty close to each other for this purpose. And I'm concluding that, you know, we can see that this is squeezing a little bit, you know, it's adapting to the right-hand side a little bit better. You know, when the points are stacked on top of each other, it's hard to see, you know, the nuances, the difference, but the blue or the black would be reasonable selections. Well, that's all I got for you. I hope you're enjoying the class. Take care and goodbye.